When you see a really clean, strong weld, you're just looking at the surface, right? The real story, the place where all that incredible strength comes from, is totally hidden. It's in this invisible, microscopic world that engineers are now learning to control with just stunning precision. So let's dive in and take a look at the hidden architecture that makes it all work.
So what's really going on here? What is it that actually gives a weld its strength? It's definitely not as simple as just melting two pieces of metal together. The secret, it lies deep inside this hidden architecture, this incredibly intricate structure that decides whether a joint is going to last a lifetime or just fail under pressure.
To really get this, you've got to start thinking like an engineer, or actually maybe more like a micro-architect. See, they aren't just joining pieces of steel. They are designing a material's internal structure from the ground up at a scale you can't even imagine, let alone see.
And the blueprint they work from? Well, that's what we call the Weld microstructure. It's the very specific arrangement of these tiny metallic grains and phases that form as the weld cools down. And this is the part you have to remember. This tiny, invisible structure dictates everything, from its raw strength and flexibility to the joint's entire performance down a line.
Probably the easiest way to picture this is, think about baking a cake, right? If you use the perfect ingredients, the exact right temperature, and the perfect mixing speed, you get this amazing uniform texture. But if you mess any of that up, too much heat, you don't mix it enough, you end up with a total disaster. Welding is exactly the same. It's just happening on a microscopic level.
Okay, so how do these micro-architects actually do it? How do they control that texture? Well, it all starts with the most fundamental tools they have, the basic dials they can turn to shape that final structure.
And it really boils down to three main levers they can pull: welding current, welding speed, and the overall heat input. Each one of these has a massive direct impact on how the metal melts and, way more importantly, how it cools and solidifies. By just tweaking these, engineers can get incredibly precise control over the final result. Okay, let's just zero in on heat input for a second, because the difference it makes is it's huge. A high-heat process like traditional TIG welding creates this really wide heat-affected zone. We call it the has. It actually damages the metal's original structure, leaving behind these coarse, weaker grains. But a low-heat, super precise process like electron beam welding, that creates a much finer, stronger structure in a much smaller zone, which preserves the metal's strength.
And we're not talking about small changes here. The difference is staggering. Research from Zhang and his team shows that using a process like electron beam welding can shrink that heat-affected zone by 50% compared to conventional methods. So it's simple. Less heat damage means a stronger, much more reliable joint.
But, it's not just about the amount of energy you're pumping in. The next level of control actually comes from the physical design of the welding tools themselves and how the whole process is set up. Let's see how that builds on those core ideas.
Okay, take friction stir welding. This is a process where a spinning tool literally stirs metals together without melting them. For this to work perfectly, every single detail matters. The exact shape of the tool, how fast it's spinning, the precise angle it's tilted at, and even how the metal plates are clamped down. Every one of those is a lever to fine-tune that final microstructure.
And look, these are not just tiny tweaks to make the weld look pretty. According to research by Kim and others, when you carefully optimize all these parameters in stainless steel, you get something called grain refinement. You're literally re-engineering the metal's internal structure to have smaller, tighter, and way stronger grains.
So just how big of a deal is this? Well, their work showed a 22.3% reduction in the average grain size. Now, in the world of metallurgy, that is a massive improvement, and it translates directly into a tougher, more durable weld. All right, so we've covered the basics. Now, let's get into the really cool, almost sci-fi stuff. Engineers are now using this advanced toolkit of techniques to get almost unbelievable levels of control over matter. I mean, we are talking about some seriously advanced techniques here. Things like applying ultrasonic vibrations during the weld, oscillating the energy beam in these complex patterns, using magnetic fields to stir the molten metal, and even adding super thin interlayers of different materials that act like a catalyst for a better bond. Let's just take one of those, ultrasonic vibrations. What's happening here is pretty amazing. As Liu and his team discovered, sending these high-frequency vibrations through the joint while it's being welded physically helps the atoms move around and mix more easily. This improved atomic diffusion is just a fancy way of saying it helps create a much more consistent, uniform bond, especially between two different kinds of metals.
And you can see the results plain as day. When you weld aluminum to titanium, this brittle intermetallic layer naturally forms between them, usually about 200 nanometers thick. That's a weak point. But with ultrasonic assistance, they shrunk that brittle layer all the way down to just 120 nanometers, creating a much, much stronger bond.
Okay, so we've talked about all these dials and smart tools and advanced physics, but let's zoom out. Why does any of this microcontrol stuff actually matter in the real world? What's the big payoff here?
At the end of the day, it all boils down to one thing. Every single one of these advanced techniques, getting that smaller grain size, that narrower heat-affected zone, that thinner intermetallic layer, it's all pointed towards a single goal: creating a stronger, tougher, and more reliable joint that performs almost as well as the original uncut metal.
And the proof is right there in the numbers. Remember that optimized friction stir welding we talked about? The final weld retained 92.8% of the base material's original tensile strength. Think about that. That means the seam is almost as strong as the solid piece of steel it's joining. That is an incredible engineering achievement.
And listen, this is not just some abstract science experiment. This stuff has a direct impact on our lives. This level of microscopic control leads directly to safer cars with stronger frames, more durable bridges and buildings that can last for generations, and more reliable electronics where every single tiny connection is absolutely perfect.
Which, it kind of leaves us with this one big, fascinating question. We're not just joining materials anymore, we're literally designing them at the atomic level. With this incredible power to control the very structure of matter itself, the only real question left is, what on earth are we going to build next?